I'm Indranath Sengupta from IIT Gandhinagar. I will be delivering a course of lectures on linear algebra. The course is divided broadly into 8 chapters, and the chapters are further subdivided into 35 modules. Let me talk about the course structure briefly. Linear algebra is the study of linear equations, and therefore we begin with linear equations. After defining a system of linear equations, we then move on to the study of row reduction, followed by echelon form, and finally we present the Gaussian elimination, which gives us an algorithm and a technique for solving a system of linear equations. In the second chapter, we introduce the notion of vector spaces. We define an abstract vector space over an arbitrary field, and then we see Rn and Cn as very spatial examples. Then we introduce subspaces. We talk about linear independence and dependence of vectors. Moving on to the notion of basis and dimension. And finally end chapter 2 with operations on subspaces, namely sum, direct sum, quotient, etc. In the third chapter, we will be discussing linear transformation between vector spaces. We will see that a linear transformation between finite dimensional vector spaces has a matrix representation with respect to chosen basis. We then introduce the notion of rank of a matrix, which is very important, especially from the perspective of solvability of linear equations. Also, we talk about determinants. After understanding the basic properties of determinants, we then move on to determinant as an alternating function, which is a characterization of the determinant function. After this basic introduction, we are more or less set for understanding the structure of a linear operator. So the fourth chapter is devoted to diagonalization of a linear operator, where we first introduce eigenvalues, eigenvectors. We talk about Cayley-Hamilton theorem. Finally, we see necessary and sufficient conditions for diagonalizability of a linear operator on finite dimensional vector spaces. Then we come to the notion of inner product spaces. We will see that the inner product structure on a vector space enables us to talk about adjoint of an operator. And this entire chapter is devoted to an understanding of what is called a normal operator. We understand self-adjoint operators, unitary operators, orthogonal operators. We see some interesting results, their structure theorems, and also we understand orthogonal operators for two-dimensional real vector space. Then we move on to bilinear forms. After understanding the definitions, we study the very important Sylvester's law of inertia and also principal axis theorem, which have great geometric consequences. And then we talk about the Jordan canonical form. That's a very important canonical form for any linear operator. And finally, we come to the chapter on modules, where we introduce the notion of a free module, rank of a module, and also torsion elements. With this, we end this course, which is supposed to be an introduction to linear algebra, and then you are all set to start the second course in linear algebra.